so far we have understood robots, industrial robots as mechatronic machine that comprises of electrical and electronic hardware, software and mechanical systems. So in the previous modules you have already seen industrial robots anatomy. You have understood its structure. We have seen how actuators are driving these mechanical links, huge mechanical links. Sensors are there, you understood sensor technology to some extent, and software is always a part of various systems which are there, ranging from control of the actuators to sensor data acquisition, processing, calculating for kinematics, dynamics, trajectory, etc., etc. From module now and on, you will be understanding robot as a mechanical system. Moving forward in today's module, that is module 4, will be doing kinematic transformation and forward kinematics. That is module 4, and in today's lecture we will be dealing mostly with degrees of freedom and kinematic transformation, especially translation. So let us move ahead. So this is the overview of this module, kinematic transformation and forward kinematics. So we'll be starting with degrees of freedom of a robot. That is very important parameter that you have seen earlier. We'll discuss about that. We'll see how Grubler-Kirchbach criterion helps us to find out degrees of freedom. Robot frames, different robot frames which are there. We'll understand matrix representation of point, frames, rigid body, etc. Transformation matrix, that is a special kind of transformation which is mostly used in robots to do transformation, mostly translation, rotation, homogeneous. We'll understand it better when we'll be actually doing it. So arbitrary axis rotation, Euler angles, we'll understand, we'll talk about that. Dhanbad-Hardenberg parameters, that is to do forward kinematics of industrial robots. Forward kinematics we'll be doing for various robots ranging from 1 DOF, 2 degrees of freedom, 3 degrees of freedom, and finally 2 industrial robots. General is special robot, which is a 6 degrees of freedom robot. So we'll be looking upon them, and all the demonstration code which will be demonstrating all these principles which are taught in this module, I'll be sharing those at the end of this module as resource. So let us move ahead. We'll be starting with degrees of freedom and kinematic transformation in this module, especially translation we'll be talking about. So yes, degrees of freedom. So that was a very important parameter that you saw when we were discussing about different performance criterion, different classifications of industrial robot. So how a robot is classified, it was also classified based on the degrees of freedom, okay, what it is. Okay, so that important parameter, let us formally define that and understand how it can be calculated. Okay, so let us move ahead. So yes, the degrees of freedom of a mechanical system, not just a robot, is the number of independent parameters that define its configuration or state. It can be alternatively defined as number of independent constraints that you can put to make a mechanical system fully constrained. So you will understand it better by doing it. So yes, let us first understand degrees of freedom as such. So any spatial object, may it be a mouse or anything. So in this space, it is free to move along vertical direction, horizontal direction, along x-axis and y-axis. Let us say this is x, this is y. So 3 translation it can do, and 3 independent rotations it can do as well. So yes, total 6 independent degrees of freedom it has. So in a space, as many number of constraints we put, the remaining degrees of freedom is the degrees of freedom of that object. Okay, so if you are you keep on constraining your object from moving. So let us say if it is a mouse pad and if it is rolling on this surface, if you can see it clearly. So what you see, it can move along this plane. Okay, so it can move along x, it can move along y. If I say it should not come out of this plane, so it cannot move along z axis that is coming out of this surface. Okay, so what else it can do? It can rotate about its axis. So altogether it can move along x, along y, and rotation. Okay, so 2 translation and 1 rotation it can do. So you got it. So why was that? Because it was constrained to move along remaining 3 things. So if I say it can move along x and move along y, it was unable to move along rotation degrees of freedom along y, rotation degrees of freedom along x. Okay, so 2 were constrained, 2 were completely constrained. Got it? And as I told, it should not leave the surface. That means it is constrained to move along vertical direction perpendicular to the plane of this plane. Okay, so it was constrained by 3, so remaining was 3. So 6 minus 3 constrained, so remaining was 3 degrees of freedom for this mouse if it is on this surface. So got it? So this is how it can be explained. Degrees of freedom of an object is always total degrees of freedom, that maximum degrees of freedom, that is 6 minus number of independent constraints which are there. Okay, so let us discuss one by one. So this is 1 degree of freedom system where you have a link connected with another link. Okay, like this with a revolute joint. Okay, so it has just 1 degrees of freedom. Why? It cannot travel like this, it cannot dislocate like this. That means it is constrained to do all 3 translation. Now let us say, because it is an axis, it cannot rotate like this, it cannot rotate like this. So 2 rotations are also constrained. So 2 rotation and 3 translations are constraints. So the body which comes next, which has initially 6 degrees of freedom, so 6 minus 5, that is 1 degree of freedom system. And this joint, you know, it can be defined by defining that particular remaining 1 degrees of freedom. If you can define the angle between the first link and the second link which is there, you have fully defined this mechanical system. Okay, so number of independent parameters, as it said in the definition also, that define the configuration or state of the mechanical system. So that is what is degrees of freedom. So 2 ways I have defined it. First, number of independent definitions that are required, and total minus number of constraints that you can put. So either way it is coming out to be 1. So now let us see what could be an example of this. It can be simply your door hinge. Okay, your door hinge is very much like this. Another similar one is this one. So what is this? This is just like a syringe and a piston. Okay, so it can be like this. It is just like a telescopic joint. It's commonly known as prismatic joint. You see normally in earth moving vehicles, this type of actuators are there which actually move those joints of huge robots, or maybe huge hydraulic systems or pneumatic systems or earth moving vehicles. So everywhere you see those. So that has got 1 degrees of freedom. Again, just by defining the displacement of this link with respect to this link, you have defined this system. So it needs just 1 parameter to completely define this mechanical system. Or alternatively, because it is a piston which is one inside the other, it cannot rotate, okay. That means 2 rotations are constrained, okay. As it is a rectangular thing, it cannot rotate about its own axis also. 3 rotations, all 3 rotations are now constrained. So how many translations it can do? It can do just 1 translation, and it cannot do remaining 2 translation also. So it is 5 constraints are there. So 6 minus 5, so it is just 1. So again similar one is there. This has got 1 degrees of freedom, although it appears if it rotates it also translates. It is what? It is a link which has a thread over here and moving on this thread. Okay, so you are unwinding it in a spiral way. So if it rotates, it also translates. So effectively just one definition is enough to fully constrain this system. If you can constrain this, you can weld it, and you don't allow the second link to rotate with respect to the first one, you have fully defined it. So degrees of freedom is 1. Okay. Similar one is other example, that is a cylindrical joint. So this is similar to a hinge of a huge gate. You see, huge gates are put like this. Okay, it is put from the top, and it can even be taken out like this. Okay, so there are two hinges which are there, which supports normally your huge gates, so that it is easy to take it out. Okay, just lift it and take it out. While putting it back, you can do it. So this is a cylindrical joint that allows rotation of the gate with respect to the wall on which it is mounted, and it also allows this vertical lift in order to take it out. So that is maybe a cylindrical joint. That is a cylindrical joint. A universal joint, so you see how many definitions you require for this. It is 2 only. So if you are not allowing it to move vertically upward, okay, you can constrain. You should also constrain the rotation degrees of freedom, rotation degree of freedom. So constraining that will fully constrain it. So 2 definitions are required. Again, a similar one is 2 degrees of freedom, that is a universal joint. This is used in moving vehicles. Okay, that is this power is coming from your engine, and this goes to your differential where 2 wheels are fitted. Okay, so you have something in between, so that it allows, while rotating your wheel, transmitting the power from the engine to the differential drive, link 1 and link 2 can bend in between. Okay, so this axis has got 2 different axes of rotation. While it can rotate about, whole of the system can rotate, okay, individually, one with relative to other one, the previous one, there are 2 degrees of freedom. One is this one, other one is this one. So 2 independent degrees of freedom. This type of joint is very common even nowadays in your screwdriver. No, you may have this attachment so that you can transfer the power, you can transfer the torque to your screw remotely like this. Okay, even if your axis is not aligned with the screw. So those attachments are there in your screwdriver set also. So you must have seen this. This is known as universal joint. It has 2 degrees of freedom. Spherical joint, this is known as a spherical joint. It has 3 degrees of freedom. It is a ball socket joint, that is there in your shoulder also. It is there in your maybe hip bone also, they are similar. Okay, so how they are connected is, you can move it like this. Okay, you can lift your arm, raise your arm like this, you can move it horizontally. So 2 are there, you see, and this your arm can rotate about its axis as well. Okay, so what do you see? It has 3 degrees of freedom. Okay, if you can constrain all 3 of them, you can fully define your joint. You can fully define your mechanical system, which is this joint. So that is 3 definitions are required. Example is your shoulder joint. So these are few examples how different joints are constructed and how degrees of freedoms are assigned to these joint, and how to calculate joint. There are 2 ways as I told. So that is all. Okay, so moving ahead, how to calculate it, Grubler-Catchback criterion for degrees of freedom is very popular. I won't go very much deeper into it, how it is derived for now. So yes, you can take it for granted, at least for planar system, it is given by n is equal to 3 times of r minus 1 minus 2p. So as it is written here. So what are those r and p? R is number of rigid bodies or links in this system, in your system, for which you want to calculate the degree of freedom. N is the degrees of freedom, okay, and p is number of kinematic pair. So if you have any background of theory of machine or maybe engineering mechanics, few chapters you must have gone through it. So kinematic pairs or joints in the system, they basically couple 2 independent mechanical bodies together in different ways. Okay, as you have seen earlier in these examples, so those were all kinematic pairs. let us use this and do some examples. You will come to know how it is used, and mind it, it is for a spatial system. If it is not a planar system, it is a spatial system like a spherical joint. In that case, you have to use formula which says 6 times of r minus 1 minus 5p. So this is for a spatial system. There are some mechanism which can go out of the plane also. So that is what. So for those you have to use the second one, this one. Okay. So yes, let us just do one example, that is a 4-bar mechanism, which is very popular type of mechanism which is used mostly in mechanical systems. I will give you a few examples also with some pictures here. Okay, so these are a few. So yes, for both the planar mechanisms that you can see, 4-bar mechanism, slider ring crank mechanism. So yes, number of links including the ground. So ground is this one. This also is a link. Okay, so this is a mechanism consisting of 1 link, 2 link, 3 link and 4 link. Okay, so number of links are 4. Kinematic pairs, you see, 1 joint, 2nd joint, 3rd joint and 4th joint. So 4 links and 4 joint. If you use the first formula for planar mechanism, so what do you see? 3 times of r minus 1 minus 2p. So it is 3 times of 4 minus 1 minus 2 4 into 4. So it is 9 minus 8, it gives you 1. How this one is made actually? This is your 1 link, okay? This is your link also. So this is your first link, okay? This is your first link, second link, this is third link, okay? And you have another link which is not visible here. It is actually 4th one, that is the slider which is sliding on this ground surface, okay, this surface. Okay, so that is 4 links. Okay, what are the joints here? So one of the joint is revolute joint R1, revolute joint R2, revolute joint which is here is R3, and one of the joint is P1. This is a prismatic joint which allows your link to slide on this rod. Okay, so there are 4 links, 4 joints for this one also. So yes, so can we do some trick over it? So there is a common query which comes along 4-bar mechanism quite a lot of time. So can it be made like this? How many degrees of freedom which are here? So you see, this also is a 4-bar mechanism with an additional support which is here, center support. It is just a parallelogram with a center support. So you can make it move like this, okay? While this will go back and forth, okay, it can go like this, okay? So yes, so how many degrees of freedom? If you just count them, so number of links that comes are 1, 2, 3, 4, 5, so 0 to 5, okay, 0 to 4, that is 5. And how many joints? You see 1 joint, 2 joint, 3, 4, 5, 6. So effectively this should come as 0 degree of freedom. But you think, you see, if you constrain this one, if you weld this joint, whole of the system is constrained. That means you just need one definition to define whole of the system. At least 1 degree of freedom should have come. So I hope you can see it clearly now. So yes, so this is what I am talking about. So what is here is this number 3 link. This link with both these joints are redundant. They are redundant, and that should be removed before you start calculating degrees of freedom. So you can have many number of such supports here. That doesn't mean all of them together should be included while calculating degrees of freedom. So mind it, you have to remove any such support, any duplicate links which are performing no function apart from some support and some different functions. Okay? Okay. So yes, now let us do some exercise further on this. So yes, this is it. So I'll come to this one at the end. Let us start with this one. Okay? This is a good place to begin with. So what you see, there are many links, you see. So best way to find out degrees of freedom for this complex system is to try doing it otherwise, instead of using Grobler catchback criterion or using number of definitions that you can define to define your system. Both the ways will prove it to be a lengthier one. So how I go for it is, you try to weld your system and try to constrain your system. The final constraint that you are able to put and this system is unable to move is the degrees of freedom. Okay, so let me just weld one of the joint. What is happening? At least this one appears to be, this is like a 4-bar mechanism. So at least this one is a 4-bar mechanism. So this piece has got 1 degree of freedom. Okay. So let me freeze this first. Okay. So what I will do, I will just freeze this one. So I will freeze this one. I won't allow this to move now. So what happens? So this point is fixed now. From the ground, this point is fixed. Okay. So what it becomes this distance is fixed because you cannot move this link. So this was already fixed, this joint is fixed, so it becomes a triangle. So this distance is also fixed. Okay, this is also fixed. Okay, so what happens now? If this point is fixed, this point is fixed, this distance cannot be changed. Okay, and this distance cannot be changed. That means even this is fully constrained. That means this any triangle is a constrained system. Okay, you cannot move it at all. Okay, so this is a triangle which is formed if you go this way. So this is fully constrained. That means whole of this is something like a single block which is attached to ground. So if I have just constrained one of them, whole of this system is now fully constrained. So if it is constrained, that means this point is frozen, this is frozen. Okay, so this solid structure which is here that you can see is fully frozen. Okay, this point is also relatively fixed. That means this point is fixed. So if this point is fixed, this was already fixed to the ground. That means these 2 points cannot move relative to each other. That means now again I can draw another triangle. So that is this one, this is a triangle. So this also is a fully constrained system. That means whole of this system is fully constrained by freezing just one of them. Okay, so this is how. So that means it has 1 degree of freedom. Okay, now let us go to the another mechanism, this one. So what do you see here? So again let us start constraining the system. This looks like a 1, 2, 3, 4. So this is 1 degree of freedom. So let me constrain one of them. I'll freeze this one. If I freeze this one, this whole system is frozen. So this was a 4-bar system. If one of the joint is frozen, the system is frozen. That means you are gone. Okay, now if this is fixed, that means this also is fixed. Okay, that means the remaining 4-bar mechanism which is here is also fixed. That means freezing just one of them, freezing thus one joint, is freezing whole of the system, fully defining the system. That means this again is 1 degree of freedom system. Okay, now let us move ahead and do yet another one. So this is a case when I will go again by constraining the system. Let me just freeze one of them. I have frozen this one. So this point is now frozen, this point is now fixed. Okay, this one is fixed, this one was already fixed, but still it remains with this 4-bar mechanism. This is a 4-bar mechanism. So what is it? This again has got 1 degree of freedom, 1 degree of freedom remaining. So even after freezing one of them, you are remaining with 1 degree of freedom. So if you freeze further, so that will constrain this remaining 4-bar mechanism. So it is fully constrained. So you need at least 1 and 2 joints to be frozen, fully defined, so as to fully define this mechanical structure. Okay, so this is having 2 degree of freedom. Done. Okay, so this is how you have to move. Okay, now the last one, which is the simplest one, but I came here last, there is a reason for it. So it is just like a serial chain system, just like your industrial robot. So in case of industrial robot, if you freeze this one, this can move, this can move, this can move. If you freeze this one, still this can move and this can move. If you freeze this one, this can move. If you freeze this one, it is fully constrained. So finally you have to freeze as many number of joints as it has in order to fully define the system. This is a serial chain system. If it has n joints, it has n degrees of freedom. So number of axes matches with number of degrees of freedom. Got it? So this is your industrial robot, which is simplest of all. So let us start with robot frames. So yes, these are robot frames. So how many frames are there in a robot and robot associated system which is there in workspace? So let us start defining. So first one is a universal frame. So this is the frame in which you may have many other robots also. You may have a robot here, you may have a robot here. So all the robot R1, R2, R3 are defined with respect to universal frame. So this is the first frame which is there in your industrial shop floor. With respect to that, all the robots are attached. So that is the first frame which is there. Okay, next one is object frame. The object that you want to handle. This may be attached with a frame here or maybe any convenient location on this object. So because it is a solid object, this frame, if once it is fixed, it is fixed. It can be placed anywhere on this object to fully define the object also. The position of the frame will define the object. Okay, the orientation of that frame will also define the object's orientation. Got it? So that is the reason. So placing one frame is enough. So that is known as an object frame. So, and then you have robots end effector frame. So this is the point which is to be taken to the object to do something, right? So that is known as your end effector frame, robots end effector frame. Okay, this is your part frame. And then you have a hand frame. So this is your hand frame. Why this is known as a hand frame and how they are different from end effector frame? So on your on top of your hand you have various tools that goes. Okay, you may be holding a pneumatic gun today to tighten a bolt. Okay, next day you may be holding just a grinding machine to do the grinding job. So everything is associated, fitted to the hands. That is also known as a robot's flange when it is delivered, and it has a specific dimension. We have talked about it already. So yes, your end effector. So this is your tool. So robot's hand is attached with a tool and tool ends with a tip which is known as your end effector frame. Got it? And then you have robot frame, you have many other joints that may also have its own frame, that is to define different links of the robot with respect to the previous link. We will talk about this later when we will be going forward kinematics. Let us move ahead. Okay. So yes, pose of a rigid body. To define pose of a rigid body, what we have is different matrix representation that we will be discussing now. So these are some of the symbols that you can quickly go through it. You can have a snapshot of this so that you can easily follow my slides. I will be using this. So all the matrices will be denoted with capital M bold. Okay, why that so? Because I have a smaller one to do something else. Let us see that one. So vectors, all the vectors. So I will be using straight letters, bold, small letters, straight, not italic, and bold. Okay. So again, all the scalar quantities, italics, not bold. Okay. They are lowercase also, light faced, and italics. Frames will be defined as italic, capital letters, unit vectors with a cap on top of it. okay, unit vectors with a cap on top of it. So I, j, k may have caps, but sometimes I can use even like this. So I can just make bold I small letter to denote I as well. So that is there. Vector joining two frames. So O is a frame, F is another frame. Vector joining two frames can be denoted as with an arrow on top of it, that is good enough, or maybe a capital bold OF should be good enough. So both are equivalent, but this is the one which I will be doing if at all it is required. Standard text is like this, that I will be following. Subscripts that are used for indexing are like this. Okay, so this is just for an example. Acceleration due to gravity and a three-dimensional vector will be denoted like small g, italic, not bold, bold G, small letter is G. That is a three-dimensional vector because vectors are here. Okay, so this is just a summary sheet that I will be following. Okay, so now let us move ahead. So yes, how a point in a space can be defined. So now we are very much used to do this. So position vector P, mind I am using the same symbol, just now I have summarized you. Okay, so this is your vector. So basically it is this vector which is the position vector of a point which is given by AX, BY and CZ, that is the coordinate of that. Okay, in matrix form from now on we will be using it like this. So a vector is now can be written as a column matrix of this kind with 4 elements. In robotics W is equal to 1 always. So a point will be represented as AX, BY, CZ in column. So effectively W becomes equal to 1. So that is your point. So point in a space will be denoted like this. Now a frame. Now a frame. So how a frame is represented? So frame is a triad of 3 vectors which are intersecting together, and the point represents the location of the frame where it is located, and those 3 orthogonal vectors, let us say if it is normal, orthogonal and approach vectors, NOA commonly known as. So there are different other terminologies also which are used for this, but I will be taking it as NOA, that is fine, or UVW is equally good. So yes, I will be using this. So N, O, A are 3 vectors. Projection of N along X is NX, N along Y is NY, N along Y Z is NZ. Okay, so that is arranged over here as NX, NY and Z. Similarly, O has got 3 components, OX, OY, OZ, that is put here. A also has got 3 components, that is AX, AY and AZ, that is another, that is the third column. So all 3 are orthogonal vectors. They are put in matrix form like this. Okay, so altogether this is your matrix form for a frame to be represented. Normally they are normal vector, orientation vector, orthogonal or orientation vector and approach vector. So they are like this. So transpose of all of these are vectors. Each of them are mutually perpendicular to each other. Now frame in a fixed reference frame. So now this frame is now displaced from here and it has come to a new location. Okay, so it is no more at the origin. So this there is a vector again with which your frame is dislocated from the origin. So it doesn't just have orientation, it also has a position dislocation. So in order to accommodate all of those, your new frame notation will be like this. It has this which actually tells the orientation of this frame, whereas the last column tells you the position vector Px, Py, Pz, that is the location of this Px, Py and Pz, that is the location of this frame with respect to your global frame. Now let us say how a rigid body can be denoted. So as I told you, if it is a rigid body, there is no relative displacement between any 2 points which is there on that body or within that body. Okay. So now if it is fixed to this rigid body, so the orientation and position of this frame will change along with the orientation and position of the object also. Okay. So what happens? So if you can define your frame's location, so that will fully define the rest of the object. So if it is a frame which is here, okay, so with which it is connected, so rest of the object points, all the points which are there on this object, as because they cannot move relative to this F, this point. Okay. So whole of that object is fully constrained if your frame orientation and position is constrained. So all this is defined, that means your frame is fully defined, it cannot rotate, it cannot translate. So your object also cannot rotate and translate, and it defines the object also. So this is exactly similar to the frame definition. So represented using point, any point on the body, and it can be any point on the body. Okay. Now what are transformation? Now that we have already defined different frame, different body, okay, how to define that, how to define a point. So transformation matrices are operators. They are operators given by 4 cross 4 matrix when applied to a position vector represented as a column matrix, as we have just seen. Okay. So that makes a movement in space through a pure translation. If you apply transformation matrix to a column vector, okay, column vector or a matrix of point, so x, y, z and 1, so it will do pure translation. We will see by example also. So it can do a pure rotation about axis. It can do combined translation as well as rotation. Using this 4 cross 4 matrix, you can do combined translation as well as rotation. That transformation can be done. How? We will see by demonstration. So in general, that is known as a homogeneous transformation matrix operator, which is given as transformation matrix. 4 cross 4 is the dimension of that matrix, 4 cross 4. So it contains these elements R11, R12, R13, so like this. And then you have a column that comes at the end. So each one of them, what are they? So R matrix, 3 cross 3 submatrix, which is here. Submatrix is responsible for rotation operation of that frame, and it is having a last column, this one, that performs the translation operation of a 3-dimensional Cartesian space vector. So let us see what are advantages this can offer. It can represent all the transformation as a matrix multiplication. If there is a matrix, okay, transformation matrix which is applied on a point, okay, it can transform this point to a new point. So this is the transformation operator applied on a point, sometimes applied on a frame also. So what it can do? It can represent all the transformation as matrix operator, because you know this can do rotation as well as translation. Okay. So it can do capturing composite transformation conveniently. It can do composite transformation, that is mix of different rotation, maybe translation in between. So you can have multiple transformation can be captured in a single matrix. So can be a point which is applied with first transformation, second one, third one, all these are equivalent to a single transformation of 4 cross 4 matrix applied on P gives you a new point. So that is what. So multiple operations can be conveniently packed in a single 4 cross 4 transformation matrix. Okay. It can change the reference frame, as I told, it can change the vector. This point with respect to frame can be changed, or your frame itself can change, point remains there. So yes, you can do multiple things. We'll see by example as we move on. Represent the configuration of a rigid body. So as you know, because rigid body is defined using a frame was nothing but rotation and translation which was there. This 3 were 0, this is 1. So this is what is your rigid body configuration. Okay, exactly it looks like your transformation matrix. So this transformation matrix now represents the position and orientation of your rigid body. So yes, so it is much easier to calculate inverse of a square, because you see transformation matrix is 4 cross 4. You can quickly find inverse transformation. We'll see why it is needed, how it is done, what are its limitations. Okay, by inverse of a square matrix, how to go for it. So yes, translation operator, using this matrix, how to do translation operation. This is just one example I'll do. So yes, pure translation, as you know, this was orientation. So I have made it diagonal element as 1 so that it becomes a unit matrix and it doesn't do any rotation operation. So only thing that remains here is this translation part. So that is dx, dy and dz. So this was your initial point at P. Finally it reaches to a new point location, that is P dash. This point is to be displaced by a distance which is d. D has projection dx, dy, dz along x, y and z direction. Okay. So this is how I want it to be done. So this is your transformation matrix that can do that. Let us see how it is. So this is your initial point which was P. Okay. And when you multiply translation matrix, this one to this point, that means you are applying a transformation to this point. And what kind of transformation is this? This is translation transformation matrix. Okay, it is pure translation. It is applied on P, you got a translated point, that is P dash. You can multiply this and check how is it. So 1 into Px, so Px plus 0 into Py, 0 into Pz plus 1 into dx. So it becomes Px plus dx. Got it? Similarly, other rows are there. And finally, the last one will remain here as 1. So yes, now this is your new position vector for this. Got it? So this is your P dash vector. So it has changed from P to P dash. It is now translated by a vector D now. Okay. So this is how this operator works. Okay. That's all for today. So next class we'll be doing pure rotation matrix, arbitrary axis rotation and how to represent rotations using Euler angles. So this is what we'll be doing next class. That's all for today. Thanks a lot.